Moving a house while living in it is a massive challenge, as we just saw with sharding. But what happens if the house itself is suddenly destroyed? That's why we need database replication, the art of keeping multiple copies of the same data to ensure our system stays online. Think of replication as having a team of stunt doubles for your data. If the lead actor can't perform, the show still goes on because the doubles are ready to step in immediately. First, let's talk about failover. In a single database setup, a crash means a total outage. With replication, if the main database fails, the system automatically promotes a copy to take its place. It's like a co-pilot grabbing the controls the moment the pilot is incapacitated. Next is read scalability. If millions of users are trying to read the same data at once, one server might buckle under the pressure. We can offload that read traffic to our copies, allowing the main database to focus entirely on processing new writes or updates. Finally, we have redundancy for geographic safety. By placing copies in different parts of the world, we protect our data from local disasters. Even if an entire data center goes offline, your users on the other side of the planet won't lose a single byte of information. Building on the concepts of availability we just covered, let's dive into the most common replication model, the leader-follower architecture, often historically referred to as master-slave. In this setup, we designate one node as the leader. This node is the source of truth and handles every single write operation. If you're inserting a new user, updating a password, or deleting a post, it must go through the leader. The follower nodes then replicate that data from the leader. Their primary role is to handle read requests. This is a massive advantage for scaling. If your app has a lot of users browsing content but fewer people posting, you can just add more followers to handle the traffic. As you can see in this diagram, the data flows downward from the leader. However, the speed of this flow brings us to a critical engineering choice regarding consistency. We have to choose between synchronous and asynchronous replication. Synchronous ensures the follower has the data before the leader confirms the write is safe, but it makes the user wait. Asynchronous is lightning fast, but there's a small risk of data loss if the leader crashes before the followers catch up. Now, think about the apps you use every day. Building on what we just covered regarding single leader setups, let's look at what happens when your application grows globally. A single leader in one location eventually becomes a bottleneck or causes high latency for users far away. That's where multi-leader and leaderless models come in. First, multi-leader setups. Think of this as having a local leader in every major region, one in the US and one in Europe. For example, users talk to their closest leader for speed, and those leaders then synchronize with each other in the background. It's incredibly fast for local writes, but it introduces a new challenge. What if both leaders get different updates for the same data? Then we have the leaderless model, often called quorum-based replication, used in databases like Cassandra and Dynamo. In this world, there is no boss's node. Any node can accept a write request. To ensure the data is actually saved, the system requires a quorum, a majority of nodes to acknowledge the change before it's considered successful. If you look at this illustration, you can see how a single client request might hit multiple nodes at once. This makes the system incredibly resilient. Even if a few nodes go down, the system keeps humming along as long as a majority is still standing. However, with great power comes great complexity. Conflict resolution is the biggest hurdle here. If two people update the exact same row at the same time on different nodes, the system has to figure out which version is the truth. Is it the latest timestamp? Or do we keep both and let the user decide later? It's a tough trade-off that we have to manage as designers. Building on the replication models we just covered, we finally reached what many engineers call the promised land data consistency. This is the goal of all that complex architecture we've been discussing. But what does consistency actually look like in practice? In an ideal world, it means every user, regardless of which node they connect to, sees the exact same data at the exact same time. We're talking about real-time synchronization where the truth is unified across the entire system. If I update my profile in New York, a user in Tokyo should see that update instantly. However, as we've seen, distributed systems aren't always cooperative. This is where the distributed conflict comes into play. When we scale across multiple nodes, we run into a fundamental wall. Network delays and node failures force us to choose. Do we stay consistent, or do we stay available? You might remember this from our earlier overview of system design. This is the core of the CAP theorem. Since we can't have perfect consistency and perfect availability at all times in a distributed network, we have to make a choice. As we move forward, we'll see that this isn't just a binary choice, but a spectrum. Let's look at how strong and eventual consistency differ in the real world. Building on what we just covered, let's dive into these two specific models. On one side, we have strong consistency, and on the other, eventual consistency. They represent the two ends of the spectrum we're navigating in distributed systems. Think of strong consistency like your bank account. When you deposit money, you expect that balance to be updated immediately across every ATM and app you use. There's no room for maybe here. The system guarantees you see the latest data right now. Then we have eventual consistency. This is more like a social media post. If I like a photo, it's okay if a friend across the globe doesn't see that updated count for a few seconds. Eventually, all nodes will sync up, but it's not instantaneous. Now, why wouldn't we just use strong consistency for everything? Well, notice this point here. To guarantee that latest state, the system has to wait for every single node to agree before finishing the task. That adds significant latency. Ultimately, it's a classic engineering trade-off. Do you prioritize blazing speed, or do you prioritize absolute data accuracy? As we move forward, keep in mind that neither is better. They just serve different purposes. Before we look at how to simulate these, let's think about a real-world scenario. Now that we've discussed the theory of strong and eventual consistency, let's see how this actually feels in a live system. Take a look at the dashboard. This is a simplified view of our distributed cluster. First, make sure the consistency level is set to strong and click Save. Notice how the dashboard pauses. It's waiting for every single server icon to turn green before telling you success. That delay is the latency cost of absolute certainty. I saw that face. Waiting for all those servers feels like waiting for a slow elevator, doesn't it? But we can change that. Switch the mode to Eventual and hit Save again. Wow, that was instant. But look closely at the servers while that successes message is on screen. Some are still updating in the background. If you click the Verify button quickly after saving, you'll see a data mismatch because the updates haven't reached everyone yet. This is the core trade-off. Do you want your users to wait for the truth or get a fast answer that might be slightly out of date? Take a few moments to toggle between the modes and observe how the latency changes as you prioritize consistency. As we move forward, keep this visual in mind. That gap where some servers haven't updated yet is what we call replication lag, and as we're about to see, it can be quite a headache for developers. Building on that headache I just mentioned, let's look at why replication lag is often called the consistency killer. It's the gap between a write happening on the leader and that same data appearing on the followers. The first major cause is physical, network latency. No matter how optimized our database is, bits still have to travel across undersea cables and through routers. This physical propagation delay is unavoidable in distributed systems. If you look at this diagram, you can see how a read request might hit a laggy follower before the update has arrived. This leads us to a very common UX problem. Imagine a user posts a comment on a photo. The write goes to the leader. Then, they refresh the page to see their comment. But the read request goes to a follower that is 500 milliseconds behind. Suddenly, their comment is gone. This is the read your writes problem, and it makes your app feel broken. To prevent these strange glitches, we use guarantees like monotonic reads. As shown here, this ensures that if a user reads version X of the data, they will never see an older version like X-1 on a subsequent read. In simple terms, we are making sure that for any single user, time only moves forward. They might see slightly old data, but they will never see the system go back in time after they've already seen a newer update. Now that we've journeyed through the intricacies of B-trees, sharding strategies, and those tricky consistency models, it's time to tie it all together. How do we actually choose the right strategy for a real-world application? Look at this selection logic flow. In system design, there's rarely a perfect database, only the right trade-offs for your specific requirements. Let's break down these 3 common scenarios we've discussed today. First, if you're building something like a news site or a social media profile where users read data far more often than they post, your best friends are indexing and replication. This keeps read latency low without overcomplicating your write path. However, as we saw when we looked at breaking the limits, if your dataset is so massive that it physically won't fit on one machine, you must look toward sharding and caching to maintain that low latency at scale. And finally, for high-value data, like the financial transactions we just covered, you cannot compromise. You need strong consistency and ACID transactions. In these cases, we prioritize data integrity over raw horizontal scaling. Before we wrap up the session, let's think about a real-world case. And with that, we've reached the final stop of our journey today. Let's take a moment to pull all these threads together into the big picture of data and storage architecture. First, we looked at indexing. As we saw with our library analogy, there's no free lunch. While indexes make our reads incredibly fast, they add overhead to every write. It's always about balancing your specific query patterns. When a single machine simply can't hold any more, we use sharding. By partitioning our data across nodes, we gain the power of horizontal scaling, allowing us to manage datasets that grow into the petabytes. Then we covered replication. This is our insurance policy, providing high availability and disaster recovery. By keeping copies of data across different locations, we ensure the system remains resilient even when things go wrong. Finally, we navigated the tricky waters of consistency. Whether you choose strong or eventual consistency, You're always making a conscious trade-off between the speed of the response and the absolute accuracy of the data at that microsecond.